Hello students, welcome to Sri Jendra's Ring Zone classes. I'm your friend and mentor for coming classes with respect to physics. This is lecture number 1 of our unit dual nature of radiation and matter. So let's begin with today's class. In today's session we are going to discuss about the dual nature of light. So let's begin. What dual nature of light and in which it shows which kind of nature. So when I say it's a dual nature of light, we mean that a light can have two nature. One, it could be a wave nature, or other it could be a particle nature. So light does exist in the form of a waves, and let us learn about the wave nature first of the light. When we define a wave, we can say that it is a mode of transfer of energy from one location to another, and the transverse wave consists of alternate crests and troughs. That's how it will transfer or it will radiate the energy. There are some characteristics explained by the wave nature of light. That is, of course, it's a reflection. So when we say reflection, it is the phenomenon in which the incident wave is bounced back from the surface of an opaque medium. This is the situation that this is the plane mirror, and this is the incident ray, and this is what we call as a normal, and this is the reflected ray. So this phenomena shows the wave nature of light. Let's look at the another phenomena. It's a refraction. What refraction is? It's a bending of light ray. It's a bending of light ray. When light ray moves from one medium to another medium is called as the refraction. So this is the one medium, this is the another medium, and let's suppose light has been traveling from this medium to this medium, and it is bending from its original path. That is what we call as the refraction of a light ray. Next, let's look at the interference of the light. It's a phenomenon in which the superposition of two or more light waves produces a resultant light intensity, or we can say energy, that is called as the interference of light. Let's look at this. These are the two sections that we generally call as a slit, and this is the optical screen from where I'm going to receive this patterns, and monochromatic planar waves will be passed through this. And if the monochromatic planar waves will be passed through this, I am having this kind of patterns. It's a black white black white black white and alternate, or it could be an maximum intensity, minimum intensity, and something like that. So this is the third. It's an interference of light. Next is the diffraction of light. It is basically a bending of a light waves at an edge into the region of the geometrical shadow. It's into the region of geometrical shadow is known as the diffraction of light. So basically these are the wave fronts. This all are the wave fronts, and that has been passed through this single slit. This is what we call as a single slit. It's a width of the slit, and from here I'm having this kind of pattern. That is what we call as a diffraction, which is a spreading out of plane waves as they passes through the hole. So this all were the proof that light can behave as a wave nature, and it can react like a wave. Now let's suppose understand the particle nature of a light. So let us learn about the particle nature of light. We can say that light is said to behave like a particles. In this nature, light will behave like a small discrete set of packets of energy. According to the scientist Max Planck's, light used to behave like discrete set of packets, and these packets are known as the he names those packets of energy as a quanta or a photons. So as you can see that this is the sun, and from the sun we are receiving the energy, and sun is delivering different packets. That packets what we call as the photons. So photons are defined as the packets of energy. One of the main characteristics explained by particle nature of light is the photoelectric effect. This will play a key role. This will play a key role in this unit. It's a photoelectric effect. Let's look at certain quick questions. The question says light has blank nature. Does it have wave nature? I should say yes. Does it have particle nature? I should say yes. So both A and B, light is having both the natures. Next, in particle nature, light is in a form of, yes, particle nature, light is in a form of discrete packets. Next, in particle nature, light performs interference, diffraction, photoelectric effect, reflection. Yes. So particle nature, this three were incorrect, and in particle nature, it will behave as a photoelectric effect. Interference, it will behave as a wave nature. Diffraction, again, it will behave as a wave nature. Reflection, again, it will behave as a wave nature. So basically it is having two natures sometimes, or probably we can say that in certain applications it can have a wave nature, and sometimes, or some in some other applications, it can have the particle nature. I hope this is clear. So to prove the particle nature and to understand the particle nature in a better way, let's study the photoelectric effect. And to understand this photoelectric effect, to understand this protoelectric effect, we have certain experimental setup so that this photoelectric effect can be studied very easily. So let's look at this apparatus. That this is the glass tube, and in this glass tube we have this cathode. We have put up and we have installed a photosensitive metal. On this photosensitive metal, a light will coming from an outer world, and on this side it is an anode, or we can say this is the collector from where I am going to collect certain electrons. As you can see, this cathode and this anode have been provided the external source. This is the external battery, that is what we call as a potential divider. What we have made an arrangement is that here emitter has been connected, which can calculate or which can measure the current that is flowing through the circuit. Here we have applied a potential difference. So due to potential difference we can definitely came to know that what would be the potential difference across what is the potential difference across this anode and cathode. I hope this is clear. Is it clear? And we have put up a rheostat over here. As you know that rheostat is a variable resistor. So as a variable resistance, it can vary the resistance, and such that current could be varied. I hope this is clear. So the thing is that light will be coming from the outer world to this photosensitive metal, and we have a certain relations. That, let's suppose, a relation is, this is HF. Should I write it one more time? Yes. So basically it is an H into F external is equals to HF naught plus kinetic energy maximum. When I say that F external is greater than F naught, if F external is greater than F naught, then photoelectric effect can start. That means if F external is less than F naught, it means there is no photoelectric effect. I hope this is clear. Is it? Are you sure? This F naught, this F naught is known as the threshold frequency. This is threshold frequency. One more thing we can have, it's a lambda external. If you This is in terms of the F external, that F external should be greater than the threshold frequency. And when it is greater than threshold frequency, photoelectric effect can start. But if F external is less than F naught, that means no photoelectric effect will occur. Same way that could be said in a terms of the wavelength, that lambda external should be less than lambda naught, where lambda naught it's a threshold frequency. This is threshold frequency. So from this it is clear that if F external is greater than F naught, the things will be go on. If F external if F external is less than F naught, nothing will move on. I hope this is clear. So we were talking about this relation, that H into F external is equals to HF naught plus kinetic energy max, or even this could be written as this is H into F external. This is equals to phi plus kinetic energy max. So this phi is the work function. This is the work function of metal, and it is material dependent property. This is material dependent property. That means each material each material has its own work function value. And first thing what you need to do is that your H into F external should be greater than phi naught, or I should say it's a phi, and phi is equals to H into F naught. So if it is greater than this, if H into F external is greater than work function, then then this photoelectric effect can start. And if H into F external is less than phi naught, photoelectric effect will not start itself. I hope this is clear. So first task will be equals to solve this, or I should say to satisfy this, to satisfy the work function. If you are able to satisfy this function, if you are able to satisfy this function, then the remaining part could be contribute itself to the maximum kinetic energy. I hope this is clear. Is it clear? Is it? So let's suppose the situation is that I have been providing a certain external energy to this photosensitive plate, and let's assume that H into F external is greater than work function. Let's assume that this H into F external is greater than phi naught, and when I assume it's a greater than phi naught, it means that photoelectric effect will do occur. So photoelectric effect will start, that is for sure. Now let's suppose what I'm going to do is that we are having a three parameters on which we can change. One is the resistance, another is the potential, and the next is the intensity. So we can change the intensity, we can change the frequency as well, and we can change the potential as well. I hope this is clear. Do you understand what I mean? So let's discuss the all the parameters. Now let's see the variations, and first we will begin with the variation of current with the intensity. So we have plotted a graph, that is a graph for the intensity versus the current. While this current, we generally call this current as a photocurrent. That means the photons will produce it. That's why we call it as a photocurrent. So as you can understood that intensity is going to increase, and intensity, and I if I plot this is as soon as I increase the intensity, current is increasing. So basically what intensity is, if you look at this certain logicality behind this, it's an energy divided by area multiplied by time. So if I'm going to increase the energy, because the area, that is the photoelectric plate, the area of that is same, time it is per second only. So basically numerically this is only the you have an option to change the energy. So what you are supposed to do is you are going to change this energy or rather you can say it's an intensity. So on this photographic plate you are applying a more amount of intensity, and as more intensity has been received by this metallic plate, or I should say this photoelectric plate, its work function has been satisfied, and the rest amount of energy other than this work function satisfaction, rest amount of energy will produce an photocurrent for us. I hope this is clear. So higher the intensity, higher the photocurrent. As soon as you increase the intensity, your photocurrent is starts increasing. I hope this is clear. This is the first variation of intensity and the photocurrent. Now let's look at the second variation. It's an effect of intensity on saturation current and the stopping potential. So what I have done here is that here two potentials are there. One is the anode potential, or I should say this is the forward potential. This is the forward potential, and this is the reverse potential. The situation is something like this, that let's suppose this is the tube and this is the metallic plate, and from here from here a light energy is going to impart on this, and let's suppose this is the situation. Initially let's suppose this is the forward potential, that means this is negative, this is positive terminal, and it would look like this, that this is a metallic plate on which this energy is going to be imparted. When this energy is going to be imparted on this, the situation will be that photons will be developed from this, and if photons will be developed from this developed photons will be moving in this direction. Why? Because this is the positive terminal of the battery. At the end of the day, these are the electrons only, because they are the photons having. Yes, so they have been collected on this positive plate. So what we suppose is that if I increase this voltage, then photocurrent will increase. And that is, this graph is showing that as soon as you increase the anode potential, yes, this is anode, this is cathode. So as soon as you increase the anode potential, this photocurrent will increasing. So what I understand is, what initially we understand this, that if I increase the anode potential, I will get the maximum current. So I start on increasing the anode potential, and it behave exactly what I think as well, that this happens and is. Now what happens, that even though I increase the anode potential, a current after certain stage is not increasing. It is at that state only, something like this. It's a straight line, some kind of. So what I understand is, this is the saturation current. Now what do you understand by saturation current? What does it mean? So when I say it's a saturation current, what I mean is that even though you are increasing the anode potential, it is not having any increment in the photocurrent, because this is the maximum possible current that can be delivered with this metallic plate on this intensity. I hope this is clear. Is it clear? So it is not going to change anywhere. So this is what I understand, that it is not the something that you keep on increasing anode potential and the photocurrent keep on increasing. There is a certain maximum possible limit would be there. That is what we call as a saturation current. Beyond that, beyond the even if you increase the intensity, current is not going to increase. Now I understand that, okay, this is done, this is the saturation current. Now what I did is that I reversed the terminal of the battery. So I keep it like this. Now this is the positive terminal and this is the negative terminal of the battery. So I have just make it a reverse potential. I have just make it the reverse potential. And when I make it a reverse potential, the thing will be that no electrons, or very few electrons, will start moving in this direction, because now this is the positive terminal of the battery. So the current keep on decreasing, and at a certain stage I have reached at certain potential where current is zero. This potential is what we call as a stopping potential. This is the stopping potential. Now, what do you mean by stopping potential? When I say it's a stopping potential, I mean, let's have a work on this stopping potential. We can say it is the potential at which even a fastest electron, even a fastest electron could not reach to the collector of plate of tube. Even a fastest electron is not having that much energy that can cross this potential and it can reach to the other end. Formula wise, it would be the maximum kinetic energy contained eh, photoelectrons would be equals to E into V naught, where it is the maximum kinetic energy of photoelectron. It's a maximum kinetic energy of photoelectron, and this V naught, it's a stopping potential. I hope this is clear. Is it clear? So this was the stopping potential. This was the stopping potential. I hope this is clear. It is a potential at which even the fastest electron cannot reach to the collector, or I should say it's on the anode of this tube. I hope this is clear. Now, very interesting part is that we have performed this same experiment with two different intensities, and I have kept that intensity 2 is greater than intensity 1. When this happens, that I understand that this when intensity is higher, saturation current will be higher. Look at this. For the first intensity, saturation current is this much only, but for the second intensity, saturation current is this only. Yes. So if I keep on increasing the intensity, saturation will keep on increasing. Yes, it is the same thing that we have discussed in the previous slide, that if you increase the intensity, a photocurrent will increases. But even though a saturation stage will be always there, that after that, if you keep the intensity same, you cannot increase the current beyond certain limit. This is what we call a saturation. But if I observe for this two intensities, a stopping potential, it is at the same location. So what I understand is that stopping potential does not vary with intensity. Stopping potential does not vary with intensity. That means even if you change the intensity, it's a stopping potential would be the same. So if I take one of the more intensity, let's say I3, then stop it could have a higher saturation current, but its stopping potential would be at the same location. Let's say this is I3, and now I3 is greater than I2 is greater than I1. Probably this is the relation. I hope this is clear. Is it clear? Is it clear? Are you sure? Do you have any doubts up till now? Is there anything? Is there anything? Are you sure? Are you sure? Great. Now let's look the third variation, that is the effect of frequency the effect of frequency of incident radiation on stopping potential. Let's look at this, how this will keep on changing. That what I have done is that same thing. This is the photocurrent, and this side on this side it's a forward potential, and on the other side it's a reverse potential. So this will be the situation. Now let's suppose I have taken one of the intensity. I have taken one of the intensity and I keep on increasing the forward potential. But here what I'm supposed to do is I will keep the intensity fixed. What I'm supposed to change is the frequency. So if I keep on changing the frequency, I receive this curve. Let's say suppose this is frequency 1. If I have taken the different frequency, if I have taken the different frequency, I have received the same saturation current. If I have taken the third frequency, almost same. But if I have, let me redraw this. It is something like this. This is for frequency 1 equals to frequency 2 is equals to frequency 3. This is for the three different frequencies, or I should say it's an three different frequencies are there, so there could be a chances of misconception. Let's have a look. This f1 is greater than f2 is greater than f3, so f1 is the maximum. So this is the forward potential, and when I keep on changing the forward potential due to this three frequencies, I have received the same saturation current for everything. Yes. But now when I switch to the reverse potential, I see that there is a one of the frequencies having a stopping potential here, another frequency is having a stopping potential here, one more frequency is having a stopping potential here. So this is the situation, that let's suppose this is the stopping potential of the third frequency because it is having the less frequency. This is the stopping potential of second frequency, it's a V02, and this is the stopping potential of the first frequency because it is having the highest frequency. So as I understand that if f1 is greater than f2 is greater than f3, that means even their stopping potential must be higher, because as you understand that kinetic energy max is equals to E into V naught that we have discussed, and this is also known as H into F. That higher the frequency, higher the potential would require to stop it, because what stopping potential is, it is the maximum required potential so that a photon or the photoelectron having the maximum energy cannot reach to the collector plate, and that is what I want. I hope this is clear. Is it clear? Is it clear? Are you sure? Do you have any doubts up till now? Do you have any doubts? Is there anything? No? So basically we have three variations. Let's look at them very quickly. A first variation is intensity is directly proportional to the I. As soon as you keep on changing intensity, your current will keep on changing. Second is the effect of intensity on saturation current. It means that if you keep on changing intensity, your saturation current keep on changing, but by changing the intensity does not, you cannot change the stopping potential. So stopping potential does not vary. With the intensity. And the third situation is it's an effect of frequency on incident radiation on stopping potential, that if you keep on changing the frequencies, your photocurrent would be the same, but your stopping potential would be the different. I hope this is clear. Is it clear? Is it Great. Now let's work for one more graph that is very, very essential. Let's suppose first we will write down the relation. We now understand this, that this is H into F external. This is equals to HF naught plus kinetic energy max. Or it could be written as this is equals to HF external. This is equals to work function phi naught plus E into V naught. Yes. Now if I divide this, this is equals to HF external divided by E. That should be is equals to phi naught by E plus V naught. Now if I want to plot, if I want to plot this for the, let's suppose, on the x-axis, I will keep the frequency of incident radiation, and on the y-axis, if I keep the stopping potential V naught, it's a stopping potential. So this could be written as V naught is equals to H F external divided by E minus of phi naught by E. This is Y, and this frequency, it's an X. So what I can write is, this is, if I write down the relation, it's a y is equals to m into x plus c, while we say that c is the intercept. I hope this is clear. Is it clear? Is it clear? Great. So how will I plot this? What can be done? Look at this. First thing, a slope of this graph. This is y, this is v naught, this is x, which is equals to m f external. So slope of this graph is h by e. I hope this is clear. Is it clear? A slope of this graph is h by e. I will summarize this. It's a slope of graph, stopping potential versus frequency is h by e. Second, intercept c is equals to minus of phi naught by e. Intercept of this graph is phi naught by e, but it is in minus intercept. It's a negative intercept. So when I say it's a negative intercept, it should look like this, something like this. And if I plot this on the negative sides, this is simply the phi naught by e. Yes, negative shows that it is a negative value. It's a phi naught by e. I hope this is clear. Is it clear? So this will give me the phi naught by e. I hope this is clear. Is it clear? Are you sure? Do you have any doubts up till now? Is there anything? Is there anything? Do you understand this? Any doubts? Any doubts? Are you sure? Great. So please remember this, that this two facts. First is the slope of graph. When I say graph, I mean a stopping potential versus frequency graph. It is an h by e, or it's an, we can say it's a slope is equals to h by e. So sometimes in a certain questions they have asked us that slope of the graph multiplied by e will give is the Planck's constant. It's an h, yes. And intercept of this graph is minus of phi naught by e. So if you want the work function, then just multiply it with e and it would be the work function. We will see the numericals based on this, but before I go with the numericals based on this, I want to discuss certain key points, that is about the photoelectric current. So first let's look at this certain key points about the photoelectric currents. So Einstein's photoelectric equation, this is the relation which we have used. HF max is equals to HF naught plus phi naught plus kinetic energy max, that has been given by the Einstein, and it's Einstein's photoelectric equation. It is based on the conservation of energy. Einstein explains photoelectric effect on the basis of the quantum theory, for which he was awarded Nobel Prize. And according to the Einstein, one photon can eject one electron only. But here the energy of incident photon should greater or equal to work function. And in photoelectric effect, all the photoelectrons do not have same kinetic energy. This is the very highly conceptual top point, that when and when we use a photoelectric effect, let's suppose we have satisfied the work function, and if let's suppose we have satisfied the work function, if we have satisfied the work function, it does not mean that all the photons they are going to be eliminate, or they are going to be produced from the photoelectric plate will be having the same kinetic energy. No, it is not like that. Their kinetic energy ranges from 0 to Emax, which depends on the frequency of the incident radiation and nature of the cathode. And last but not the least, the photoelectric effect takes place only when photons strike bound electrons, because for free electrons energy and momentum conservation do not hold together. I hope this is clear. So this is about the bound electrons. This is about the electrons that have been binded with certain orbits, and we are providing them an energy. It will jump to the higher level, and then it will come back and it will radiate certain photons. I hope this is clear. Is it clear? Is it? Now let's discuss laws of photoelectric effect. This is very, very important to understand and to remember. This is laws of photoelectric effect. Let's understand first. We say that the photoelectric current, it's a photoelectric current is directly proportional to the it is directly proportional to the intensity of incident radiation. So photoelectric current is directly proportional to the intensity of incident radiation. That means intensity increases. Intensity is directly proportional to the photocurrent. This was the first variation that we have discussed today. That it means intensity increases, photocurrent increases, and so on. I hope this is clear. Let's discuss the second point, second law. It is that the saturation current is found to be proportional to the intensity of incident radiations. Whereas stopping potential is independent of given intensity. So saturation current is there, which is found to be proportional to the intensity of incident radiation. But stopping potential does not depend does not depend on the intensity. This was the variation in the second graph that we have see the second variation. Let's work for the third important law, that we can say there exists a certain minimum frequency. It's a certain minimum frequency we call as a cutoff frequency or threshold frequency. We call a cutoff or threshold frequency. So if f external is less than f naught, or or lambda external is greater than lambda naught, then there will be no photoelectric emission. There will be no photo emission take place. So every time when you have been asked the questions based on this photoelectric effect, always just first check it, that whether I need to do it or it is just the case of the no photo emission. If it was the case of no photo emission, then you don't need to do anything. You just deny that there is no photo emission, and that's it. Question has been over. So always check that whether this is the case where photo emission will take place. If your answer is yes, then think for the next question. I hope this is clear. Is it clear? Is it is it clear? Always work for this in this manner only, because many a times they are going to pull you at some other region, and they will ask you that what would be the, if intensity is this many times, what would be the current and everything. But first you need to check whether my intensity is changing or not changing. First thing is to ask myself is, does photo emission will take place? If its answer is yes, then only think beyond this, that what will happen if intensity is increases and saturation current is so and so and everything. I hope this is clear. Now, uh, one of the next law that is linked with the above point only, that if f external is greater than f naught, or I should say a lambda external is less than lambda naught, then then saturation current saturation current is independent of frequency, but but it but I should say stopping potential but stopping potential depends on the stopping potential depends on the frequency. As we know now, that higher the frequency, higher the stopping potential and everything. So first I have checked it, that if f external is greater than f naught, or lambda external is less than lambda naught, that means this is the cases where photo emission will surely take place. If this was the case, then I can say that saturation current is not dependent on frequency. Saturation current is not dependent on frequency, but stopping potential is going to be dependent on this. I hope this is clear. And last but not the least, let's have a check. It says that the photoelectric emission is an instantaneous It's an instantaneous process. It does not take a very good amount of time. That first light energy has struck to it, and then photo emission will take place, and then photocurrent will develop. No, this is not a time. This is approximately less than 10 to the power minus 9 seconds or less. Yes, all this has been achieved. So it is a, we can say that, or and we can claim it, that this is an instantaneous process, and it does not take any amount of time. It does not take any amount of time to, so that we can understand that this has done. It is just the instantaneous process. I hope this is clear. Is it clear? Is it clear? So now, are you ready with the questions? Are you ready with the questions? Just stick to the basics. The first basic is that always check whether photo emission will start or not. If photo emission will start, then you think for the rest of the task. Otherwise, simply say no, this is not possible. That's it. Bye bye. I hope this is clear. Is it clear? Now let's begin with the numericals. So let's begin with the first question. It says that the threshold frequency of material is 2 into 10 to the power 14 hertz. Find out work function. Find out work function in electron volt. This is requirement. How will you do this? The threshold frequency has been given, that is the f naught is given. It is a 2 into 10 to the power 14. I required a phi naught, which is a work function. So as we know, it's a phi naught is equals to h into f naught, and let's put up the value and get it done. It's a phi naught is equals to h into f naught. The h, which is a Planck's constant, which is, it's a 6.62 into 10 to the power minus of 34 multiplied by, it's multiplied by 2 into 10 to the power 14. So if I do this, it is simply the 0.8275 electron volt. That's it. You did it. Great job. I hope this is clear. Is it clear? Is it? Are you sure? Do you understand this? Have you? Great. So ready for the next question? Are you ready? Let's have a look. The next question. The next question says that light of wavelength, it's a light of wavelength 2000 Armstrong falls on metallic surface whose work function is 4.21 electron volt. Calculate the stopping potential. So how will you do this? They have given the light of wavelength is given, it's a 2000 Armstrong, and it falls on the metallic surface whose work function is given. What I need to find out, I need to find out the potential, stopping potential, that means. So how will I do this? I understand that it is the h into f naught, that is equals to hf plus e into vs, that is what we call as a stopping potential. So if h into f naught, it's an h into c divided by lambda naught, is equals to hf, that is work function, plus e into vs. So first check it that does hc by lambda naught is greater than function, If this is the task, if this is answer of this is yes, then you can move further. If answer of this question is no, that means no photoelectric effect take place. Please always do check this. Always do this. Yes, I have checked it out and answer of this question is yes. So now I will proceed further that H into F naught, this is equals to HF plus E into stopping potential. So HF naught minus HF is equals to E into Vs, and from this Vs is equals to HF naught by E minus HF by E. So if I put up the value, if I put up the value and get this done, this is could be written as H by E multiplied by F naught minus, so this is basically a work function. This is equals to the work function by E minus of this is H into F external. I have written it reverse. Give me a moment. It should be something like this, that H into F external is equals to HF naught. So this is H into F external minus HF naught. This is equals to work function. So this is HC by lambda external minus phi naught is equals to E into Vs. So just put up the value and get it done. How, what is your data? And it's an H which is 6.63 into 10 to the power minus of 34. Lambda external was given, it's a 2000 Armstrong. It's a 2 into 10 to the power 3 into 10 to the power minus of 7 meter. Next, what else you required? It's a work function that is required. Work function, it's 4.21 ev. It's multiplied by 1.6 into 10 to the power minus of 19. Now it's a volt. Yes, it's a work function. And what else? Nothing. So get it done. You will find that this work function will be equals to, or stopping potential will be equals to 2 volt. Sorry, I hope this is clear. This was the answer. So please make it calculated on your own. You need to do this. You cannot simply leave it. I hope this is clear. Is it clear? Is it clear? Do you understand this? Are you sure? Great. Let's work for the next question. Suppose the question says that find the maximum velocity of an electron emitted by light of wavelength lambda incident on the surface of a metal, on the surface of a metal of of work function phi. How will you do this? They said find the maximum velocity of an electron emitted by light of wavelength lambda incident on the surface of a metal having the work function phi. So what I understand is that lambda has been given, so it is the hc by lambda external is equals to work function phi plus it's an half mv square. I want the maximum velocity, so it's an hc by lambda minus of phi is equals to half mv square, and from this it's a 2 by m multiplied by hc by lambda minus of phi to the to the square root is equals to V max. I hope this is clear. That's it. You did it. Great job. I hope this is clear. Is it clear? Is it? Do you understand this? Are you sure? Do you have any doubts up till now? Is there anything? No? Are you sure? So ready for the next question? Are you? Let's have a look. The next question. Now the question says that a light of wavelength light of wavelength 2475 Armstrong is incident on barium photoelectrons emitted describes a circle of radius 100 centimeter 100 centimeter by a magnetic field field of mag flux density which is 1 by root of 17 into 10 to the power minus of 5 Tesla. Find work function of barium. It's they have given that E by M would be equals to 1.7 into 10 to the power 11. So go through the data once and think how should we proceed. They said that light of wavelength is given, and so this lambda external is equals to 2475 Armstrong is given, is incident on a barium, and photoelectrons describes, that means photo emission does take place, a circle of radius that they are emitting will define, or that will moving in a circular path, and that circular path is having a radius of 100 centimeter, and that magnetic field is given, it's a flux density, that means magnetic field is given, it's a 1 by root of 17 into 10 to the power minus of 5 Tesla. So what I need to do, I need to find out the work function. How should I do this? What do you think? So what I understand, or what I think, is that I should look like this. It's an HF external should be equals to work function plus kinetic energy max. So I am having this because I have been provided the lambda. It's an hc by lambda external. So this data has been given. Work function I need it. Kinetic energy, how will I find it? So if it was the case of the circular motion of the charged particle in the magnetic field, what we have done in the fourth unit, it was a moving charge and magnetism, is that if you have remember this, it was the situation that this is the center, and the particle were moving in the particle were moving with mass v, velocity v, this radius r, due to magnetic field. And this is the case of the magnetic field, that's, let's suppose they are within the plane. So this was the case where it's an mv square by r is equals to qvb. So this vv has gone, and from this mv is equals to qbr. Now kinetic energy, it's a kinetic energy could be written as it's a p square by 2m. So this is equals to q square b square r square divided by 2m. This is the kinetic energy. So now let's look at the data. What is given, that even E by m is given, that means q by m is available, magnetic field is given, and the radius is given. So all the data has been given to calculate the kinetic energy. And if I am able to calculate the kinetic energy of it, it would be something like this, that if I put up the value that says, because q by m is given and everything is given, so from this kinetic energy could be calculated. It would be into the maximum kinetic energy would be in certain terms of joule. If you calculate it, let's give it into the joules first. It's an 8 into 10 to the power minus of 20 joule, and if I convert this to an EV, this will be zero point 0.5 EV. Now the situation is that Hc by lambda external is equals to work function plus kinetic energy max. So from this, work function is equals to Hc by lambda external. This lambda external, it's a 2475 into 10 to the power minus of 10 minus kinetic energy maximum. This is equals to zero point 0.5 in EV. So put up the value and get the answer. Your answer should be 4.5 electron volt. I hope you got this. Is it clear? Is it clear? So can you do this kind of questions? Can it be done? Can it be? Do you understand this? Have you got this? Are you sure? Great. So ready for the next question? Are you ready? Suppose the question has been something like this, that give me a moment. Yes, the question says that light of frequency 1.5 times the threshold frequency, 1.5 times the threshold frequency is incident on photosensitive material. Photosensitive material. Now, if the frequency is halved and intensity is double, the frequency is half and intensity is double, find new photocurrent. This was the question they asked. How will you do this? What could be done? They said that light of frequency 1.5 times the threshold, 1.5 times the threshold frequency is incident on a photosensitive material. That means your F external is equals to 1.5 times of F naught. F naught is the threshold frequency. Now if the frequency is half, that means if F dash is equals to F external by 2, it's a new frequency basically, it's a 1.5 F naught divide by 2, which is equals to 0.75 of F naught, and intensity is double, that means I dash is equals to 2I. What is the photocurrent? So what I understand is that now my new frequency, it's a 0.75 F naught. New frequency is 0.75 F naught, and that means this F dash is less than F naught. It's less than threshold frequency. If this is less than F naught, that means no photo emission will take place. And if this was the situation, then there would be a no photocurrent, whatever could be the change in the intensity, because photo emission not is, if photo emission not going to start it, we don't need to think beyond this, that what happens and how this will happen. I hope this is clear. Is it clear? Is it clear? Great. So ready for the next question. Let's look at this question. Suppose the question says that when photon of energy 3.8 electron volt falls on photosensitive material photosensitive material having work function of 2.8 electron volt. Find kinetic energy emitted find kinetic energy emitted by photoelectrons, or I should say find kinetic energy of emitted photoelectrons. Yes. How will I do this? What could be done? What could be done? So let's first think is that H into F external is equals to first task is to satisfy work function plus rest of the amount is the maximum kinetic energy. So HF external, this is when photon of energy this has been reached, it's a 3.8 eV. Work function, it's a 2.8 eV. So this is equals to plus kinetic energy max. So its kinetic energy max, will be equals to 3.8 eV minus 2.8 eV. This is equals to 1 eV. This is equals to 1 electron volt. But please keep this in mind, this is kinetic energy maximum. So if you look at the kinetic energy of all the photoelectrons, then it could be vary from 0 to 1 eV. It is not the case that all the photons that is being produced, would be having this energy. It can keep on changing. It can keep on changing from 0 to 1 eV. I hope this is clear. Is it clear? Is it? Are you sure? Do you understand this? Is it clear? Great. Please keep this in mind because we are always in hurry to judge that it is of 1 eV and all photons would be having the same energy. No, it is not like this. I hope this is clear. Great. So, ready for the next question? Let's have a look. The question says that if the frequency of incident light is doubled, how will maximum kinetic energy will change? So what they have done is that incident frequency has been doubled. They have doubled the incident frequency and they want us to calculate that how the kinetic energy will change. So let's understood this, that suppose this was the situation, HF external, it's equals to work function phi naught plus kinetic energy max. I hope this is clear. Now the situation is if they double this frequency, so it's a H multiplied by 2 into F external is equals to work function remains the same. It is not going to be changed. It's a work function plus New kinetic energy, I should say it's a kinetic energy dash. So let's suppose understood that this is the relation number 1, this is the relation number 2, and if I need to compare this, that this kinetic energy is greater or this kinetic energy is greater, or it's a twice, it's a thrice, it is greater than twice, less than twice, what happens? So let's try to do the analytical study that work function could be written as 2 into h into f external minus of kinetic energy dash. This is, let's say, third relation. If I replace the value of this work function into the first relation, it is something, it's an hf external is equals to, it was the situation work function plus initial kinetic energy, I call it as a 1. So now and the work value of work function was 2 into hf external minus kinetic energy, we call it as a 2. This is our requirement. So this is hf external is equals to it's a 2 into hf external minus ke2 plus ke1. So this is the situation, then I will shift this to here and shift this to here. So this will be, it is something like that, kinetic energy 2 would be equals to 2 into hf external minus hf external plus kinetic energy 1. So this is equals to 2hf minus hf, this is equals to hf external plus kinetic energy 1. I hope this is clear. This is the kinetic energy 2. Is it clear? Is it clear? Yes, no, yes. So basically if you see this, it becomes more than double. It is not just only double, it becomes more than double. I hope this is clear. Is it clear? Are you sure? Are you sure? Do you have any doubts up till now? Is there anything? Is there? No? Great. So let's wind up this session over here. This was all about the introduction to dual nature and photoelectric effect. This was the first part of this unit. It's a dual nature of radiation and matter. In the next session, we are going to discuss about the dual nature of the matter. So before you tune into that, please go through this very carefully. Revise this in a very good manner. And once you do it, this is very easy to get or to have a command on it. So please do as many questions as possible and even go through the NCRT of this unit once, because this is the requirement. Please go through it. This all are the theoretical sessions, and which requires a very good amount of theoretical knowledge too. Thank you. Have a good day. Take care.